Okay, so we'll continue where we left in the last class. So we had arrived at this situation where we had four unknowns but only three independent conditions for equilibrium, and then we said that it is a statically indeterminate system. Now there are two ways to move ahead. Okay, and I mean, actually three. One of them is that we can just give up and not solve this problem ahead, and that's one way, of course. But the second way is that we look. So one way is to give up. The second is to take a highly idealized model, okay, which is statically determinate. Okay. On the third part is to develop a theory for statically indeterminate. Okay, so just to make your life slightly hard, we will not take up this option. Okay, we will not give up. The second part of highly idealized model is something which we will do immediately, but overall objective of our course, in this entire course, what we want to do is to actually do this, okay, so that we don't have to solve problems which are highly idealized and hence much away from reality. So the objective of the overall course is this: we will take up a idealized model right away so that we can solve and get our first estimations of the answer, and gradually over the period of this course we will develop theories and concepts through which you can actually solve a statically indeterminate problem which we are confronted with. So let's do this for now, okay, and we'll proceed in the later chapters for the very same problem as I've told before, and try to add and learn more theories and so that we can solve it eventually. Okay, so for a highly idealized problem, let's do this. So we say that this MC is an ambiguous, okay, MC will go over here, okay. MC is an ambiguous part of this. It's basically the moments due to the bolted joint, and clearly we can't ignore this like we could in a friction in a pin. So for a bolt we are not able to, but this is what we say: if the bolts are loosely fitted and are not tightened, in this case MC can be ignored. Now this again, as I've said, is a high idealization that the person who is in charge of tightening the bolts didn't tighten it enough and hence it was loose. Obviously it was dangerous. I mean, the safest word which we would want to use over here. But the good part is that because it's loose and not tightened enough, there can be a rotation around here, okay, a free rotation around here, and hence this bolt can actually be idealized as a pin. So this bolt over here can actually be idealized as a pin in this case. Okay, So that is what you see in figure 1.24. It differs slightly from where we had left, and this is a simplifying assumption which we are taking. What I would want you all right now is to not just see it as a whimsical assumption. Please see that there was an actual need for taking this assumption. Okay, you were actually up against the wall, in the words of the author of the book. So you had to do this in order to solve it right now with the knowledge which we had. And as I've said before, as the more knowledge we gain, we wouldn't actually need to take assumptions like this. Okay, so in this case, when this bolted joint can in fact be taken as a pinned joint at C, in this case, let's see how easy it becomes for us. Okay, so in the free body diagram of 1.24b over here, there will be forces FB, FC, and FD. Okay, so you have FB, FD, and FC. And this is, in fact, I mean, if you have seen, we have actually slightly modified the problem by not taking the bolts. Now, you have already read about the three force member. In this case, this frame can be taken, or the bar CD for that matter, can be taken as a three force member. We'll do that slightly later on. So the directions of FB and FC are known. So in this way, the directions of FB and FC are unknowns. Taking advantage of our previous experience with figure 1.23, we show that the free body diagram of bar BD can be written like this. So coming from here to here is the same as was from coming from here to here. Okay, we have done a 2-point member. This bar BD was taken as a 2-point member, and hence FB and FD have to follow this pattern. Okay, now taking advantage of our previous experience, we show that the free body diagram of bar BD is this. Since this is a 2-force member, FB must be along the line BD. And now you return from here to this for the entire frame with this information. So it looks like this. FB will clearly be in this direction. Okay, FD we are not showing now because I mean it's not an internal force. So this is for the whole frame. This D over here was only for CT. That's why you had an FD over here, but FD does not appear in this because now we are referring to the whole frame. Okay. So FB is known, the direction is known. I mean, I don't say that the magnitude is known, and 20 kilonewtons was as it is. I mean, we don't, it's an external force acting on this frame, and it seems the stage is all set for us to actually use this 3-force member idea on bar CT. So if you have one force on CD in this form, this is CD, okay, the other force in this direction, the third force, which is FC, has to be in this direction so that they can all be intersecting at this one point D. So this is just a concept of a 3-force member which we have learned before, and all this is done essentially, as you know, for equilibrium, in the sense both the external forces and the moments have to get cancelled. Okay, so that is what we have, and this diagram which you see is what we can easily solve. Okay, so you can take the moment about B equated to 0, you will get the value of FC, and then you can take the summation of forces in the y direction, and then you'll get a value of FP. Okay, so that the moment you take the moments about point B, FB will not appear in that equation. only FC and this 20 kilonewton will, and once with that you have FC, then you can just use the force balance and you'll find FB and FC. So this is how you would solve this problem, the so-called more simplified way of solving the problem, and this is how we are getting after the. But keep in mind, we'll take up the very same problem later on, and we'll keep on taking up until chapter 8 in your textbook, and we'll develop a much more rigorous theory so that we don't have to do this. Otherwise, I mean, there's no point in learning this course. Okay, so right now you can get away with this, but not so much later. Okay, let's take another example which will continue with us for a very long time in this course, and this is about something called the truss structure. So the picture which you see on your screen is that of the Havra Bridge. I mean, there can be any other bridge, but just for the scale of it, we had put it up over here. So this is something called a truss structure, which you see on your screen, the image. And these structures typically are used in bridges or even many other sort of systems which you have to carry load. Okay. Now we take a not such a grand truss structure. We take a very simple truss structure over here, which is example 1.4, again solved in your textbook, but we would want to go through this for the sake of reasonings which are involved. We are trying to sort of alter our way of thinking about an engineering problem, and that's why we are going through this word by word and line by line. Okay, so that there's no hurry to rush forward to get the answer. Okay, so you have a pinned truss is shown in equilibrium. So you have this pinned truss structure. It is a plane structure. That means all of it is in the plane which is of your screen, consisting of relatively rigid links connected by pinned joints. So there are rigid links connected by pinned joints. Okay, what does it do? It carries loads at E and F. Okay, so at E it carries a load, at F it carries a load, point load. Okay, it's a point load which is acting at these 2 points. It is pinned to a rigid foundation at A. So this, as you see, is a rigid foundation at A. There's a pin joint again over here, and is supported on a roller at B. So this is a roller, and you may already be aware of what a roller does. It will allow a displacement in this horizontal direction, but not in the vertical direction. Okay, so only in the horizontal direction a roller will allow its motion. Okay, and the primary problem is to determine the forces at A and B due to the load. So you have to find the forces at here and here due to the loads at E and F. Okay, and then a secondary problem is to be able to find the forces in the individual links, meaning what is the force in this, what is the force in this, what is the force in this, and so on. So the primary part is to find forces at A and B, and then the forces within the links. Okay, so this is a truss structure problem, and as you see, the application of this problem is huge, and we are taking a simple example just to see how a truss problem is solved. Okay, now the first part, to be able to find the reaction forces at A and B, what we do is we isolate the entire truss in the free body diagram. So you can have a look at that over here. So the entire truss structure is taken like this, and we have so what is the external force? It is the force at A, and B, because it's a roller, you have taken a force in the vertical direction. So let's see what are the idealizations which have taken. Okay, what are the assumptions which we have taken? Assumptions in coming from here to here. Okay, what are the assumptions? What first, just like the last case, the weight of truss is neglected. Okay. Now you can always wonder, I mean, look at the Howrah Bridge and say, how can you ignore the weight of truss structure like this? But do give us some time in this course, and you will see why approximations like that can be taken. Okay. I mean, it doesn't look like a very light structure, but the whole point is it will become light or less with respect to something. Okay. And we'll see that as we move along. But for now, let's just go with this. Okay, so weight of the truss is neglected. Now you trace the periphery of the isolated system. We have included the loads at E and F. Okay, so E and F loads you have already taken. At B we have idealized the roller support by showing a vertical reaction FB. Our rationalization, so reason for doing this from this, okay, let's just look this. The reason this can be done as this, just a vertical force, is that a roller is designed for horizontal motion. So roller is designed for horizontal motion. Okay. And I mean, this can be the rollers also of your, say you want to move a big box of Almira or a refrigerator or a washing machine, anywhere where you have a roller. The purpose is that it should support horizontal motion. Hence, it should not provide much horizontal resisting force. Okay, because if it was providing a lot of resisting force, then we wouldn't put a roller, right? We'll just put a sliding sort of a situation. You know that rolling is easier than sliding, hence you put on rollers. So that is the reason that this horizontal force has to be quite less, and that is why you are able to ignore the horizontal force over here compared to the vertical one. That's the reasoning why you are taking. We do not say at any place that it is frictionless. Okay, we don't say it is frictionless. All we say is that it should not have a lot of horizontal resisting force, and hence it is easier to ignore that. Okay, so let's move ahead then. Look at the pinned joint at A. We have shown a reaction Fa which passes through the pin. Okay, now why is it passing through the pin? Ideally you are aware that it should actually, if this is the pin, it should actually pass through some distance. Okay, we have seen this in the previous class from problem 1.10 as well, but we have ignored because this contribution of the moments is actually quite less. We just assume that this only passes like this. Okay, so just like from the previous case, we have made an idealization by neglecting the possibility of a frictional moment. We neglected the frictional moment, not the friction itself. Okay, I hope that point is clear. It was clear then, it should be clear now. Our rationalization is that even if there is some friction, the smallness of the pin implies that the effect of the friction motion about the center will be small. So that's the reasoning which you have used. Now, since the since the truss is a planar system, it's lying in the plane of your screen, the loads are acting on the screen, and hence by the same logic as the previous one, FA and FB must also lie in the same plane. Okay, and because it's a planar system, they must satisfy planar system in equilibrium 1.7 and 1.8. Okay, now remember what 1.7 and 1.8 were. It was about the summation of all the external forces in a planar system, and this was the summation of all the moments due to the external forces about an arbitrary point in a planar system. Okay, now this, it seems, is enough to solve the problem. Okay, now the method which is given in your textbook is first to take the moments about A and equate it to 0. By doing so, you will have no contribution by FA. Once you, through this method, you can find FB. Once you find FB, you can just use 1.7, and which is the balancing of forces in the horizontal and the vertical direction, and you will get FA. So that solves the first part of your problem, in which you had to find the reaction forces at A and B. Okay. Now let's think about this problem from a more engineering perspective. I mean, what you have done now was just to find the forces, and that's the end of your problem. But no, now you have to start thinking like a person who is designing this. What do I mean by designing? Okay, and you will obviously at some point have a course in machine design. I think that is an extremely important course, and the purpose is this, that you now know that you have a system which goes from A to B, and then it has to take up a load of this and this. As a designer, your job is to decide few things. You have to decide on what should be the material of this link, what should be the thickness of these links, and questions like that. The idea is that none of these links, or even for that matter a joint, should break when it is subjected to a load like this. And you can see that over here. The designer of this Howrah bridge had taken into account of a lot of things. How many vehicles and people would be there on the bridge at any given time. And none of these links should be failing, which you see in this figure. Okay. So that is what is the job of a designer over here. And you can keep on taking as realistic cases as you would want. In the sense, you have to take care of how the wind flows. Okay, you have to take care of other environmental factors like humidity, rusting, and so on. And the overall objective is that the structure should stand and serve its purpose. So designing this little structure, we will keep our scope slightly limited to our easier examples, so that we can understand and appreciate, and eventually sometime in life perhaps you should be doing things like this. Okay, big great things. Okay, so the designer of this truss, however, is interested in how the loads are transmitted by various uh, members, so that he can be sure that each member is strong enough. We don't want any of these links to fail. Okay, so you would want to find the forces in each of them, and you know from your own knowledge, I mean, if you take a steel wire and then you take a wooden matchstick, the wooden matchstick, if you try to pull, it will break at a much lower load. So if you want to see which kind of what is the force, you can hence design then accordingly. I mean, you can take a different material, take a thicker material, and so on, once you know how much forces each of the links have to sustain. Okay, so we'll try to do that now. So as an illustration, we show in figure 1.27, there you go. Okay, figure 1.27, you have taken this link AC over here, okay, and AD. We have taken just two of them. Okay, I think this is D, not exactly marked, but this is D. Okay, okay. Now, if figure 1.27a and b free body diagrams are shown, of course, the weights of the bar and the frictional moments around the pin joints are neglected. Okay, frictional moments about the pin joints are neglected, the weight is neglected, and hence this free body diagram should be good enough. 2 force member, as you know already. Same over here, and in figure 1.2c we have just taken the pin A. Okay, this is the pin A. So on this pin A you should have a force FAC, you should have a reaction force AY. Okay, and you have a FAD which is acting over here. Okay, so these are the three situations which you have, and because the pin is in equilibrium, you can do a force balance over here. Okay, which is according to equation 1.7 for this one. Okay, and you will do it in both the directions, and you should be able to find the value of FAC. FAC is essentially the force in this member. Okay, similarly you can find the force FAD and so on in this case. Okay, so you will see that AC is actually in compression, AD is in tension, so one of them is being pulled, the other is being pushed, and then as a designer you can see, well, this material has to take up a force of say 70 kilonewtons, so what should be the material I should use? Okay, what should be the specific alloy which I should be using? Okay, because every material is not the same, and so on. Okay, so you may have done problems like this before, but now we are doing this revision of our thought process, and in which we start thinking more like engineers. Okay, and your courses of material science which you should be studying and machine design should be able to very well link with what we are doing. Okay, now there is one other example, which is example 1.6 of a screw jack, which I am not discussing in this course. The reason is I believe that that can be much better dealt in your course in machine design. So you should definitely read up about screws on bolts from that textbook of your machine design, wherever and whichever book it is, and then come back to example 1.6 to study this. You will be able to appreciate it much better. Okay, you may have done a fitting experiment in your workshop in which you rotate the vise and then the clips come closer to each other so that your workpiece can be held. So that is the mechanism which is used commonly, and you can have a read at it yourself. You should actually have a read at the whole book, but I am just specifying this one because it is very closely linked to your course in machine design. We'll here take up something uh, more relevant to us. So we'll take up this example, which is what 1.7. Yeah. So this is about a step ladder. Okay, you may have seen this, a step ladder in which you sort of stand somewhere over here and you want to reach a certain height by so any repair work you want to reach for something which is at a higher, so it's a step ladder, and then there are steps through which you can climb and reach there. Okay, so you have a light step ladder. I should write the language given. Light step ladder, You wish to now estimate the force on the link AB. Okay, you want to find the force on the link AB. When a man of 800 newtons, roughly about 80 kilograms, stands on the top of this ladder. Okay, and the purpose can be the same. You want to find the force in AB so that you can choose a material, choose a thickness, so that this will not break. Because you see, I mean, if this AB breaks, it will be a big problem for the person standing on C. Okay, so as a designer, as an engineer, this is what you are trying to do. You are trying to find what the force is there, and then you can use your concepts of designing to find out what material and what dimensions I should use over there. Okay, so we'll begin with the idealizations and then lift off some of the idealizations and see how we are doing. Okay, so let's see. We begin this example by selecting the ladder and idealizing its characteristics in figure 1.30b. So please look at this B figure. You have taken up this ladder, and obviously 800 newtons is acting at point C vertically downwards. It's the weight. Then there are two reaction forces shown, N1 and N2, acting at E and D. Okay, so let's see what is the assumption coming from here to here. Because it is given in the question that it's a light step ladder, what we are doing is we are taking the bars to be weightless. All the bars which you see, okay, all of them are weightless. That's the first thing. The joints at A, B and C, joints at A, B and C, which in most ladders are relatively free, have been idealized as frictionless pinned joints. Okay, so joints at A, B and C are idealized as frictionless pinned joints. So we will take up friction somewhere, okay, in this problem, but we want to, just so that we can focus on one part of it, we are taking it as a frictionless pinned joint. Okay, now if you look at table 1.2, is it table 1.2? Yes, table 1.2, column C, you will see what are the forces for a frictionless pinned joint. Okay, now let's see the interactions, idealized friction pin joints at A, B and C. Okay, now the interactions between the legs and the floor, which in practice can have a large variation in friction, have been taken as frictionless. So E and D are taken as frictionless. And that is why you have only reactions N1 and N2 on this. Now you can always definitely, and you should question, how can we take assumptions like this? The objective is that you start with these assumptions and then you start removing them and see how your answer changes. And that is what we are going. We are trying to study idealization. Okay. So these idealizations permit us to obtain a good first approximation of the actual case. Okay, this is clearly not the actual case. B is not the actual case of A, but it will give you a first approximation. And the ladder is and what is the actual case? You see, the ladder is light but not weightless. The floor is definitely not frictionless, completely frictionless, and the pin joints are reasonably free but not completely frictionless. So in reality, the pins are not frictionless, the floors are not frictionless, the ladder is light but definitely not with a zero weight. However, B is an approximation. B is the idealization which you try to get to your first approximation. Okay, and then you will see that if you want to take friction over here at E and D, how much the answer will change. We'll see that later on. Okay, first consider the frictionless case. You isolate the link AB over here, and since again it's a 2 force member, you show the forces as is shown over here, equal and opposite, lying along AB. So obviously with C itself you cannot find the value of AX, which is your desired force in the link AB. Now you want to isolate the other parts. The first part which you can isolate are these two parts, leg of the ladders. So the pin force at C is represented by the unknown components Cx and Cy. So this is due to the pin. Okay, 800 is already shown to us over here, and similarly over here you will have a Cy and Cx, so that the joint at C actually does not have I mean it's an internal to that joint, but now since you are taking it separately you will have to show Cx and Cy's separately in these two bars. Okay, so note that the unknown forces Ax, so Ax again is shown as is from the link, and N1, N2 as you go along. Now note that the unknown forces Ax, Cx and Cy are shown consistently according to Newton's third law. That is the action of the leg C on the link AB is Ax and so on, while the action of the link AB on the leg C is Ax. So you have done this several times in your first year course in mechanics. Now you don't actually know what is the direction of Ax. Okay, the whole point is that this system is all consistent. So Ax, if it comes out to be positive, it means this is correct and hence everything around it will be correct. If it comes out to be negative, everything around it will come out to be accordingly. So you have to be consistent in your taking of these unknown forces. Okay, now the isolated free body in 130.1.30D is a planar system, and then you know what to do. You have to use 1.7 and 1.8. So what are the unknowns? Let's see. You have Ax as the unknown, you have Cx as the unknown, you have Cy as the unknown, and is there anything else? And you have N1. Okay, this is the unknown in the left ladder, and similarly you will have four, and so these are four unknowns, and similarly you will have four unknowns in the right ladder. I mean this is for this one, and for the right ladder you will again have Ax, Cx, Cy and N2 this time. So for each isolated part you have four unknowns, and 1.7 and 1.8, if you remember, give you three conditions, independent conditions. Okay, so you cannot obtain Ax only by taking only one of the legs as a free body, but you can get enough equations by writing the equations for both the legs. So this is something which you can do yourself. You can write the equation 1.7 and 1.8 for both of them, and since there are common terms in both, you should be able to solve this equation. Okay, so another way clearly is to make use of 130D, this one. Let me just remove it over here, in which the entire structure is isolated. the external forces N1, N2 and 800 Newton load must satisfy the equilibrium conditions. So you will be able to find the value of AX in this case, and that would be 267 newtons. I mean, you can see the actual solution in your textbook, but we are discussing only the theoretical concepts behind this. Now we want to take friction between the ladder and the floor. So we want to take this condition. By doing this, we are getting, so we had taken three idealizations. Let's call this as I1. Let's call this as, sorry, I1 is the weightless, I2 is the frictionless pin joint, and I3 is the no friction between the ladder and the floor. So we want to now get rid of, so with this we get AX as 267 newtons. I'm keeping this number so that we can compare it when we get rid of one of these idealizations. Okay, there you go. Okay, so what we want to do now is get rid of I3, in the sense now we want to consider friction between the ladder and the floor. And if you look at figure 1.31, now you have F1 and F2 shown in this. Okay, now if you apply 1.7 on this, you will find that F1 is equal to F2. Okay, and you will get a value for N1 and N2. Okay, so N2 in this case would turn out to be 533 newtons. But you are already aware that the friction, that the sense of the friction force is not defined. I mean, we just know that the maximum value is this. Maximum value is what we'll be dealing with, but we don't want to do. We don't want to take. You just give a value like that. Okay. So the law of static friction tells us about the upper limit and so on. You already know. So let's take the coefficient of static friction as 0.2, and for that you should have F1 is smaller than equal to 0.2 into 267. That would make it as 53.4 newtons, and F2 would be smaller than 0.2 into, oh, I shouldn't be using into, right? We have already gone through this. This should be 533. Okay, and this should give you 106.6 newtons. Now, since F1 and F2 have to be the same for equilibrium, we have to say that F1 is equal to F2 is smaller than equal to 53.4, the lesser of the two, right? I mean, F2 can take up a value of 100, but F1 can't. But since both of them have to be the same at any given time, this is the criteria which is satisfied by all the three situations. Okay, and you know that the friction cannot, I mean, since we don't know the sense of the friction, we have taken a direction, but we don't really know. So the actual answer can be 53.4 newtons to 53.4 newtons for any f, so for this f1 direction which you have taken, this is what you should have. Okay, depending on the previous history of the ladder, I mean if you're already trying to push it, what would happen and so on. So you have this value of f1. So I mean, if the sense, if you were trying to open the ladder or you were trying to close the ladder, then the sense of friction would change, and that's where this is coming into the picture. Now, can we solve for AX now? AX, also called the new AX. New AX in the sense in which the friction between the ladder and the ground is taken. Yes, of course, you can take the moments about C and equate it to 0. You should get AX is equal to 267 plus 2.5 F1 newtons. And this would mean that if F1 is lying between minus 53 point, here, between minus 53.4 to plus 53.4, AX will also lie between 400.5 newtons and 133.5 newtons. Now look at the beauty of this as an engineer. You have to find a material or design a thickness such that the link AB can sustain a force between this and this, provided these two approximations I1 and I2 are reasonable. You have already got rid of I3 now. Okay, now see how much it compares. If you did take I3, you were getting AX as 267 newtons. If you got rid of this idealization I3, you have got AX, which is actually at maximum almost twice. It was a quite a big number, 267 into 400. I mean, it's okay. So less than twice, but you have a big number over here. So the reaction, the force inside the link will actually be much higher if you consider friction. It can be much higher depending on how the ladder, whether it's being opened, whether it's being closed, and so on. Okay, so that is the difference which an idealization makes to your answer as an engineer. So if you had devised and if you had taken a material which would sustain this amount of thing, and in reality the floor would have friction, your material would have broken because the actual force was more. Okay, so this is something which you have to really think about and get comfortable with the way we deal with this. Okay, so we leave here, and we'll be beginning with the concepts of chapter 2, which is about the deformation mechanics of deformable bodies. And one more point which I must make is the following: please read the textbook very carefully, one by one, word by word, line by line, from section 2.1, which is introduction itself. Okay, go through that reasoning, attend the lectures which is through these recordings, and in between you can play and pause as you want. Go back to the textbook and read again as you are following through. You should be able to follow the reasonings behind this. Okay, that is the single most important thing which you should learn. Please don't try to skip any of these two steps. Okay, so we'll learn the theory and the problems will be continuing parallelly in a separate fashion. So let's meet in the next lecture. Thank you.